Hello friends, welcome to Engineering Funda family. In this video, I will explain lead compensator with great clarity. Before I start with my explanation, let me tell you the outlines of this video. In this video, first of all, I will discuss about basics of lead compensator. After that, I will explain S-plane representation of lead compensator. After that, I will derive maximum phase condition of lead compensator. After that, I will explain lead compensator using electrical network. And at last, I will explain Bode plot of lead compensator. So let us start this video with first agenda, that is basics of lead compensator. In lead compensator, we add positive phase with input signal. Means output phase leads with respect to input. So in lead compensator, we add positive phase with input, means it is having lead network characteristics. If we have lead network, then output phase leads with respect to input in lead compensator. Let me explain that by waveforms. If you observe here at input, we have sinusoidal input. At output side, here we have phase lead with respect to input. So here we have phase lead by angle phi with respect to input, means this is lead network. And always remember, in lead compensator, we have high pass filter characteristics. Means here low frequency signals are getting attenuated and high frequency signals are amplified. In Bode plot, I will explain how exactly we have high pass filter characteristics. By Bode plot, you can easily understand how gain and phase response is there. See, in lead compensator, we add positive phase with input, means output phase leads with respect to input. Now, I'll explain S-plane representation of lead compensator. To design lead compensator, we need to add one pole and one zero in left half plane of S-plane. If you observe, here we have S-plane, where with horizontal axis we have real value and with vertical axis we have imaginary value. This is left half plane of S-plane. To design lead compensator, we need to add one pole and one zero in left half plane of S-plane. And always remember, with lead compensator, see this pole that will be having higher value compared to 0, means this 0 that will be there towards right side of this pole. Here if you observe, this 0 that is having value of minus 1 by t, while with this pole we have value of minus 1 by alpha t. Here value of alpha is lower than 1. Then only this pole can be over this side of this 0, right? With lag compensator, you will be observing here we will be having pole and here we will be having 0. And in lead compensator, pole will be available over here and 0 will be available over here. Here with pole, value is minus 1 by alpha t, where this alpha is lower than 1. Based on this pole and 0, we can identify transfer function. See, transfer function of lead compensator will be 1 by alpha into 0, that is there at minus 1 by t, means it is s plus 1 by t, divided by we have pole, that is s plus 1 by alpha t, right? And always remember, in lead compensator, this alpha value that is lower than 1. Here 1 by alpha, that is amplification factor. Now I will derive maximum phase condition of lead compensator. To derive maximum phase condition, we need to substitute S is equals to j omega in transfer function of lead compensator. So here we have transfer function of lead compensator. In this, we need to substitute S is equals to j omega. If you substitute S is equals to j omega in this, then transfer function will be 1 by alpha into j omega plus 1 by t divided by j omega plus 1 by alpha t. Now With this transfer function, I will identify phase and magnitude. So phase will be phi, and always remember phase is positive for zeros and phase is negative for poles. Here for 0, phase is positive, that is tan inverse of imaginary component divided by real component. Imaginary component is omega divided by real component is 1 by t. So this t will come in numerator. And phase of pole is negative. So that will be minus tan inverse of imaginary component divided by real component. So that will be omega divided by 1 by alpha t. So alpha t will come in numerator. So this is phase of lead compensator. And here value of alpha, that is lower than 1, that one should know. Now I will identify magnitude of lead compensator. Magnitude m, that will be, here we have constant, that is 1 by alpha, and for numerator magnitude will be square root of imaginary component square plus real component square, that will be omega square plus 1 by t square, and in denominator magnitude will be square root of imaginary component square plus real component square, that will be omega square plus 1 by alpha square t square. Now I will identify maximum phase condition. See, maximum phase phi, that one can have by differentiating phi with respect to omega, and it should be 0. If you differentiate this phi with respect to omega, then here differentiation of tan inverse omega t, that will be constant t divided by 1 plus square of this, that is omega square t square, minus differentiation of tan inverse omega alpha t, where constant is alpha t, divided by 1 plus square of this, that is omega square alpha square t square, and that is equals to 0 to get maximum phase. Now we need to simplify this. So here if you observe, this t, that is getting common and it is getting multiplied with 0, and see this alpha divided by 1 plus omega square alpha square t square, that will go on other side, and if you do cross multiplication, then over this side we will be having 1 plus omega square alpha square t square, and over this side alpha into 1 plus omega square t square will be there, means it will be alpha plus alpha omega square t square. Now if you take this alpha on this side, then we'll be having 1 minus alpha, and if you take this omega square alpha square t square on other side, then here we will be having omega square t square common, and here we will be having alpha into 1 minus alpha. If you carefully observe, this 1 minus alpha, that is getting cancelled from both of the sides. So we will be getting value of omega. See, omega square will be 1 divided by t square alpha. So omega, that will be 1 divided by t square root of alpha. So this is what the frequency at which we have maximum phase, right? Now we have maximum phase frequency. To get maximum phase, we need to substitute this frequency into equation of phase phi. Here if you observe, we have phase phi, that is tan inverse omega t, where instead of omega we need to substitute 1 by t square root of alpha. So here we will be having tan inverse omega t, where omega is this, so t will get cancelled, and here we will be having 1 by square root of alpha minus tan inverse of, we have omega alpha t, where instead of omega we need to substitute 1 by square root of alpha. So t is getting cancelled, and in numerator we will be having square root of alpha. Now we need to simplify this. See, this equation, that is similar to tan inverse A minus tan inverse B, that is A minus B, that is 1 divided by square root of alpha minus square root of alpha divided by 1 plus AB, means that is 1 by square root of alpha into square root of alpha. Here See, this is getting cancelled. So in denominator, we have 1 plus 1, that is 2, right? And in numerator, you will be observing 1 minus square root of alpha into square root of alpha, that will be 1 minus alpha, and divided by 2 is there. Along with that, square root of alpha will be there. So this is maximum phase of lead compensator, right? Now I'll explain you calculation of magnitude at maximum phase. To get the magnitude, here we need to substitute this frequency in the equation of magnitude, right? Now I will substitute this omega m into this equation. So magnitude will be 1 by alpha into square root of, instead of omega square, we need to place square of this. So that will be 1 by t square alpha, right? And in denominator, instead of square root of omega square plus 1 by alpha square t square, here we have omega square, where we need to place square of this, that is 1 by t square alpha plus 1 by alpha square t square. Now we need to simplify this equation. If you carefully observe, here see 1 by t square, that is getting common from numerator and from denominator, and that is getting cancelled. So here we have square root of 1 by alpha plus 1, and here inside square root we have square root of 1 by alpha into 1 plus 1 by alpha. So square root of 1 by alpha plus 1, that is getting cancelled, and simplified resultant output will be square root of alpha divided by alpha, that will be 1 by square root of alpha. So here we have magnitude for maximum phase. Here we have frequency for maximum phase with lead compensator, and this is the equation of maximum phase with lead compensator. These are the essential equations that we will be using it in future coming videos to solve some examples. Now I'll explain you lead compensator using electrical network. You can observe here we have R1, R2 and C connection for lead compensator. Here I will derive transfer function, that is V naught t divided by V in of t, right? To derive this, first of all, I will simplify this circuit in frequency domain. See, in frequency domain, in Laplace domain, this V in of t, that will be V in of S. This VO of t, that will be VO of S. And this capacitance C, that will be 1 by SC, right? Now, first of all, we need to simplify this much impedance. Here you can observe we have impedance that we need to resolve. Let us say this much impedance is Z1. So that impedance, that is a parallel combination of impedance due to C and impedance due to R. So here impedance due to C, that is 1 by SC, and impedance due to R1, that is R1, parallel combination is 1 by SC into R1 divided by 1 by SC plus R1. If you take SC as LCM over here, then in numerator we have R1, and in denominator we will be having 1 plus SC R1. So that is this much impedance, right? Now to get transfer function, we need to apply voltage divider rule. If you apply voltage divider rule, then output voltage V naught of S, that will be input voltage, that is V in of S, and here we are measuring voltage across R2. So in numerator we will be having R2, and in denominator we have this impedance plus this impedance. Here this impedance is Z1 and this impedance is R2, right? So now we have transfer function V naught of S divided by V in of S. Here we have value of Z1, that is R1 divided by 1 plus SCR1 plus R2. Now we need to simplify this equation further. If you take LCM of this, then this term, that will be multiplied with R2 over here, right? And in denominator, we will be having R1 plus R2 plus R1 R2 as C, right? Now we have this equation that we need to represent in standard form. You can observe here we have standard form like this. I will try to represent that transfer function in this form, right? So here what I'll do is I will take CR1 from numerator. So here we will be having V naught of S divided by V in of S, that is equals to CR1 R2 in numerator. So here we will be having S plus 1 by CR1, right? And if you observe denominator, then from denominator we can take R1 R2 C common. So here we will be having C R1 R2 common. So we will be having S plus R1 plus R2 divided by R1 R2 C, right? Now here you can observe this is getting cancelled and we need to simplify this further. So in numerator we have S plus 1 by CR1, and in denominator if you carefully observe, then here we have 1 divided by CR1, right? So that is R1 plus R2 divided by R2, right? So if you carefully observe this term, so that is similar to standard form. You see in standard form, in numerator we have S plus 1 by T, and in denominator we have S plus 1 by alpha T. So here what is T? Here our T is CR1, and this is what alpha that we have, that is R2 divided by R1 plus R2, and as I have told you, alpha value should be lower than 1, right? It should be lower than 1. So this is how we can represent this transfer function of this electrical network in form of lead compensator, right? So standard form that I have explained over here, right? That is this, for which I have derived maximum phase condition. Using this maximum phase condition, we can solve many questions as well. And here we have this electrical network in form of lead compensator as per this standard form, where T is CR1 and alpha is R2 divided by R1 plus R2, right? And obviously that will be always lower than 1. Now I'll explain you Bode plot of lead compensator. See, in lead compensator, earlier I told you that we have one pole and one zero, right? And if you observe, see this pole in S plane that is having higher value compared to 0, right? So in terms of frequency, always remember pole is having higher frequency compared to 0. So if you want to plot that on Bode plot, then here see in Bode plot, here we have gain plot. So at this frequency we have lower frequency. See, as you go in this direction, frequency will increase. And in lead compensator, frequency of pole that should be greater than frequency of 0, right? So here we have a frequency that is lower frequency. So but obviously this is a frequency that is associated with 0, and here we have corner frequency that is associated with pole. Now if you observe, here we have a slope that is 0 dB per decade. After corner frequency 0, what happens? Slope is added by plus 20 dB per decade. So this line that is having slope of plus 20 dB per decade, right? And after pole, slope is reduced by 20 dB per decade. So here we have 0 dB per decade slope. So that is how frequency response is there with lead compensator as per pole and 0, right? Now here if you carefully observe, this is a frequency response that is similar to the frequency response of high pass filter. Earlier I told you lead compensator acts like a high pass filter, right? So based on this frequency response on Bode plot, one can understand it is acting like a high pass filter. If you observe the phase response, then here phase response in which phase is added due to lead compensator. So you can observe here phase is added over here, and here we have maximum phase. Here we have maximum phase phi m, right? And that is happening at the frequency omega m. This frequency omega m and phi m that I have already derived in this video, you can observe frequency phi m, that is 1 by t square root of alpha, and phi m, that is tan inverse 1 minus alpha divided by 2 square root of alpha. And if you design this lead compensator using this electrical network, then in these components one should be having value of t, that is CR1, and alpha, that is R2 divided by R1 plus R2, by which you can achieve this type of frequency response where we are adding positive phase. Always remember, lead compensator adds positive phase in the system. That's why it is lead compensator, and it is acting like a high pass filter. And in lead compensator, alpha value, that is greater than 1, while in lag compensator, beta value, that is lower than 1. Otherwise, equations are identical. You can observe my last video based on lag compensator, in which I have derived equations, and both equations are same. Like if you observe the frequency equation, magnitude equation, and phase equation, so all the equations are same for lag compensator. Only difference is in lag compensator we have beta, in lead compensator we have alpha. Beta value should be greater than 1 and alpha value should be lower than 1. That is only the difference which we have, right? I hope you have enjoyed this session. Still, if you have any confusion, just place that in comment section. I'll be happy to help you. Thank you so much for watching this video.